sages use.
Can I also use the...
You can use
Yeah.
this one. You can also,
Yeah, I think it's...
you can hang it around your neck.
Yeah. Okay. Yeah, so I think everyone can hear me? Yeah. So, good morning, everyone. My name is Yuhao Zhang from the Technical University of Munich. My supervisor is Professor Patrick Bucher, and my director advisor is Dr. Matthias Duschek. And as presented, my talk today will be about using Bayesian optimization for mixed variable problems in the natural sciences. So, as a bit of an outline, this is the structure of my presentation, where I'll first motivate the background, and then the actual Bayesian optimization process, and then how to make it work for mixed variables. Then I will go into a bit more details into the actual implementation, and followed by benchmarks we conduct, and then the results. So, the background. So within the context of materials discovery and optimization, that's what I mostly focus on. We have two main methods of addressing these problems. So the main one, which I think maybe, at least from the talks I've been to, most people are familiar with, are the simulation-based ones. So this could be potentially functional theory-based, or dynamic-based, or we can directly use generative AI models. These are quite data hungry. What's most important is that all these theoretical models then produce theoretical results, meaning that you need to validate these through experimental means. And on the other side of the pond, you can then do experimental like research instead. So this involves synthesis and characterization, meaning that your data is inherently noisy, and then producing these data is time-consuming, meaning you have limited data, and then to optimize materials or materials discovery, you often have some sample space that you want to sample from, where you have this one. Okay, it's not that. Okay, anyway. So meaning that you rely on heuristic sampling methods, so these can be intuition-based or based on some physical insight that you have on the material, or do you use these predetermined sampling methods? And now the question is, can we somehow combine the best of both worlds? And the answer is yes, and that's where Bayesian optimization comes in, which is defined as a sample-efficient adaptive strategy for optimizing black box objectives. And I'll show like a brief example, but what you need to know is just that it's consisting of two main parts. So a probabilistic surrogate model, so this is any probabilistic kind of a predictor that you have, which most commonly is a Gaussian process in the natural sciences, but of course it can be a random forest or even a Bayesian neural network. And then the second part, which I argue is one of the most important parts, is this what's called an acquisition function. So this is actually what will suggest to you the next experiments to make and what is actually the kind of brains of this method. And some examples of the most commonly used is this EI and LCD. So now just to show an example workflow. So for example, let's consider you have some 1D optimization problem in this X1 domain. So this could be some, let's say, chemical concentration, and then the true objective is this black line, and then you give your one or two data points to fit through it, producing this blue prediction, and then the shaded region is the uncertainty. And let's say here you want to minimize this problem. So you don't have to know this algorithm here, but you iteratively essentially start from data point, you fit the model, and the green line here is produced by your acquisition function, and you feed the model the data that your acquisition function wants, and then it updates the model predictions, and therefore also updates your next acquisition function location. And then you just rinse and repeat, and you add a data point fit, add a data point fit, and see here converge. The model doesn't know that, so we know that it's converging the global minimum. And then we go on until you converge. And, well, I've pressed the button a lot of times, sorry. But, so essentially, as you can see, the example here is in a continuous space. However, optimizing these problems in non-continuous space is not standard. And by non-continuous space, I mean spaces that include continuous variables, integer variables, discrete variables, and categoricals. So discrete variables are just integer variables that have non-equidistant spacing. And the reason for this is because optimizing the acquisition function for generating this new location in these mixed spaces is non-trivial. So there's non-standard methods for handling this. And that's what makes this mixed field particularly tricky. And that's where we implement a method by Dalton et al. From Meta. So essentially, they use this reparameterization method, which maps the discrete non-continuous variables into a continuous theta space. So Z is your non-continuous, theta is your continuous space. And as you can see here, even though, let's say, the landscape here in black takes integer values, your model is still continuous, however the acquisitions are then restrained to these integer values. So your model kind of inherently knows about the discreteness in your space. And then it can resample. But as you notice here that with this method and some noise in your data, actually inherently kind of out of the box, if you just use it, it has these resampling issues where it resamples a location that you've already resampled and it just gets stuck in this loop, which is not what we want. And resampling issues we found is attributed to issues such as the fully discrete landscape and or these highly fluctuating landscapes and with the presence of noise, which is very common in experimental settings. And the reason why, at least we believe that the authors didn't mention these resampling issues is because they are from the computer science world where their functions are noiseless, right? And then they don't really also encounter these resampling issues. And also their domains were always mixed. It wasn't really used in these fully discrete spaces. So this is a problem, and therefore for real life kind of workflows, we need to address them, and that's where we present this modified BO workflow for mitigating these resampling. So essentially you just do normal BO, however you do this redundancy check where you see if you have a redundant candidate, then you kind of omit that candidate and switch to a purely exploratory acquisition function, and then you continue the BO loop. So this kind of fail-safe check ensures that, okay, if there's no redundant candidates, you just do a standard BO loop here. If there is redundant candidates, then you don't actually get trapped in these resampling states. All right, so that's the kind of mixed variable method and workflow we propose. And now, just as a practical illustration of using this mitigation workflow of the same kind of problem you see here, now at this third iteration of sampling, when we switch to pure exploration and not resample this point, you see the actual model resamples a new point here, so we don't get trapped in this resampling regime anymore. So now the time for the benchmarking. We construct a synthetic test function that we aim to kind of model what objectives would be encountered in real life optimization tasks in the natural sciences, meaning that we don't have like 100 local minimas and the landscape is relatively smooth with one competing minima and is symmetric. However, we want to benchmark this like more robustly, meaning that we want to do different dimensionalities and different discrete levels. So for example, to illustrate, this is the 1D representation of our buttermilk squash benchmark, and if we then discretize it, it will look like this. In the 2D continuous case, this is the contour map that you saw, it looks like this, and then when you discretize it, the integer values, it looks like this, right? So now, kind of taking this logic to the higher dimension, then we can construct this function map, where the functions that you saw, the 2D case corresponds to here, where 1C is like, okay, all of the variables are continuous, and then this one corresponds to here, where okay, all of the variables, meaning all the dimensions are take integer values. So here you can see we go to the 6th dimension, and then all of them take discrete values, and some of them take half integer, half discrete values. So yes, this is one of the main benchmark suits that we do. So we want to be quite comprehensive, and that actually produces results that experimentalists can use from, because often theoreticians take benchmark from here, 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 and it's not very comparable. And then the second is, so while we also benchmark on this buttermilk squash function, we want to answer some following questions. Okay, what's the best model, kernel model that we use? So do we have priors, or BF by term kernel? Okay, which acquisition function is the best? What kind of kernel design? And this is usually omitted in these mixed variable BO models where they just take some arbitrary kernel design, whereas we actually also want to optimize it and tailor it towards these natural science problems, or like landscapes encountered in the natural sciences. And then after we actually then optimize or get this best kernel design, we then do some stress testing. So we have this really highly discontinuous problem. So this kind of would represent the extreme cases that we encounter where maybe your material undergoes some phase change where there's a disrupt, like boundary change in the properties. So this is what we call dust 1. So this is a bit of an easier problem. And then there's dust Dust2, where it's just basically a larger space, so it's a bit more complex. And yeah, this is kind of to push our implementation to the limit to kind of see if it has any weaknesses or not. So now to the results. So here I show the butternut squash results, where this is the convergence criterion depending on the evaluation budget. So here I've kind of truncated all of the functions, meaning that, okay, for two-dimensional problems, we initialize each model with 5 initial points, and then we let it run for 35 iterations, single point acquisition iterations. For 3D problems, 10 and 80. So meaning that, okay, 25% evaluation budget at the like 3D problem means that, okay, like how many of the models have converged if we only let it sample, if we do, for example, 4D, 25 data points, so 25% of the iteration points. So here I benchmark way more models. It's around 18 models, I believe. But here are just the 4 main ones that are most important. So Sobol is just Sobol sampling your design space. And you can see that it performs quite poorly if it's randomly sampled in this design space, whereas this meta model is quite interesting. So this is the original kernel design used by Dalton et al. From Meta for their implementation. And they argued that our implementation works with any arbitrary kernel design, and they just propose this arbitrary composite kernel. And we kind of disproved them that actually no, actually the kernel design is very important, even though you come up with this nice implementation, because our kind of best kernel design, which is called this and also GAM, works the best. And this KR model is also interesting. So this doesn't follow our implementation. This is another state-of-the-art mixed variable GP implementation that does some other rounding technique. So we also kind of, as a comparison, beat on the state-of-the-art with our kernel design. And yeah, so this is the squash function. So you can see at like 100% iterations, our budget is like basically converge on all of our problems. And already at like 70% budget, most of our functions converge. And now to the dust results. So then we chose this best Boston model, so that's the MVP, and we then actually used our resampling mitigated BO to compare to the Sobol or like a vanilla BO without the mitigation and random forest surrogate BO. And you can actually see that with this resampling mitigation, our model converges to lower values, especially with the dust2 case, which is more complex. So it's interesting to see that Sobol offers very competitive results because it actually is such an easy space. So that concludes the work, and then for future work, we have this boss package that I'm going to implement this implementation in, and you can scan it with the developer of, and then kind of implement it with other functionalities. And yeah, so you can scan this. And then thanks to the MCML and ACS at Alto and my group, and I'll take any questions. Thank you.